this is the K-Nearest Neighbour Python tutorial. We're going to walk you through a nice simple example of how to implement K-Nearest Neighbour in Scikit-learn. This is a really good example of a simple supervised learning algorithm. So ideal if you're getting used to new algorithms in machine learning. It's a really good one to start with. So let's do it. Okay, so what you're looking at here is a Jupyter notebook. You've probably come across these before, but these are really useful ways to build, code, and add your own notes together. So you can add Markdown and code, or Python code, simultaneously. So it's a really good way of sort of demonstrating these results or keeping notes on what you're doing. And we're going to use these throughout the course. Right, so let's do that. So we're going to start by saying, okay, we'll have the KNN walkthrough. Okay, so all these Jupyter notebooks will be tidied up, saved for you online so you can download them. I do really recommend actually typing out some of these yourself, maybe the smaller bits, because actually that process helps you learn how to do Python, whereas just copying my code, you probably won't get as much from it. So just a sneaky trick that really helps me when I'm learning new things. We're going to add some code. We're using Python here. Really good thing about Python and other codes is there's lots of rich libraries that we can utilize and use. We're going to use 4 here. That's going to be pandas, which is ideal for manipulating data or data frames. We're going to use NumPy, which is a really useful package for doing lots of different arithmetic. Scikit-learn, which is a really rich machine learning package, which you can use all sorts of algorithms. And then also matplotlib, which is going to be used for plotting out the results. So we're going to start by importing pandas. And we do that by saying import pandas as PD. So like PD is now an abbreviation to pandas. And then import numpy as NP. And then we'll just run this cell. So hopefully, the first time you run it, it might take a little while, but yes, we got a tick. So these libraries are now fired up. Right, so we're going to now load our dataset, pull a URL address. So there's lots of really good datasets online. Here, particularly at UCI, there's a really nice one which is about snails called Abalone. So there's about 5,000 different measurements of sea snails. And we're going to use this in this data set. So what we're going to do is from this URL address, using a pandas data frame, we're going to write abalone is pandas, and we're going to read the CSV directly from the URL address, and then we're going to add an additional variable which says header none, which identifies that there is no header. So there's no labels at the top of the columns in the file. Because there's no labels in the columns, we're going to actually have to add those. So I'm just going to get the list here because I can't remember them always. So this bit of code then says, well, okay, now we've got this data frame Abalone. We're going to assign the columns, so dot columns, to a whole list, identify each of the columns as a different variable. So we have sex length, diameter height, whole weight, sucked weight, Viseria weight, whatever that is, shell weight, and the rings. In this data set, because we want them all to be floats, i.e. we want them all to be numbers rather than just labels, we're actually going to drop the sex column. So we do this by using the useful pandas command called drop, and then we give the label, and we say the axis is we're expecting equals 1, which means that we're expecting to drop a column, right? So we do this, and what have I done? Unexpected indent. Okay, I've got a cheeky indent there, so you've got to be careful with indents in Python. Okay, brilliant. So we've got the data set, hopefully it's loaded fine, but we want to check that, so always good. I remember my teacher when I first learned programming was always like, if in doubt, print it out. So here we go. Abalone.head will show the first 5 lines of what's in this data set. So what we have here, we have indices. So there are many more than this, there are about 5,000, but there's indices of the first 5 rows, 0 to 5, and then length, diameter, height, whole weight, etc., etc. So all the measurements. that I mentioned in these columns. That looks all good. That's just a summary of the first 5 columns. So maybe also it's quite good to look at some statistics of that. Pandas has nice operations that allow you to calculate certain statistics. So you can do abalon.describe as a method, and we can run this code. And what you get for each of the columns now, we get count, which is how many there are. So in this data set, it's not 5,000, that was wrong, there's 4,177. You get a mean, standard deviation, a min, a max value, and then you get the percentiles, right? Which is, useful data to see. Also really useful to make sure that the data isn't really corrupt. If it was a max value or a min value and there was a default value, if data was missing, you might see it in these values, or you might see a very large standard deviation. For example, if they use a default value of 999 for a missing value. So really useful. If in doubt, print it out. Really good mantra to have when looking at new data. So what we're going to do in this challenge, what we want to do is, from these attributes that are easy to measure, we're going to want to predict the age of the sea snail. I'll try and say it right. So how we do that is, this final column is rings. So just like trees, the number of rings that a shell has indicates how old it is. But to measure this, the shell has to be chopped, dyed, and then measured. It's laborious. It's not very good for the snail. So the idea is, can we make a prediction model from the simple measures like length, diameter, height, which are really easy to measure, and estimate the age with some accuracy? So that's the challenge. So what we're going to do is, we're going to take our data set and we're going to say, well, our data set is going to be the input variables. So we'll have abalon drop rings. And then we're going to drop the whole column. So what our input training data is going to be is the abalon data set minus the final column, which is the thing that we're going to predict. And then our y, our target values, are going to be abalon. Let's do this properly. Rings, right? So this means we're going to try and learn a machine learning model which has inputs of x, and then we're going to try and hit targets of y. We can see it's going to be supervised because we've got labeled example data. Perfect. Okay, so one key thing that we must think about is that in K-Nearest Neighbour, we will be looking at relative distances of components of the input. But the problem is, length, diameter, height, weight are kind of different in measurement, how they've scaled. Some of them have different units, like weight is different to a length. So what we need to do is, we need to normalize our input data, our x data, so that we kind of have a standardized measurement which doesn't really have any units in it. This is super standard in lots of machine learning algorithms and really good practice to get into. So to normalize it, I'm going to add a bit of markdown here. I'm just going to write a formula in LaTeX for you. Don't worry about the LaTeX, but you'll see it. So what this is saying is, I've got my data x, and if I subtract the minimum and then I divide by the maximum values of each column minus the minimum values of each column, each of these variables, which I've called x dash, will be readjusted so they live solely on 0, 1, so they'll all be scaled the same. Luckily, you can do all these operations with pandas and numpy together. So to do this, I'm going to call this x norm, which indicates that x has been normalized. I'm going to write x minus the minimum value of x divided by numpy max value of x minus numpy min value of x. Okay, and then just to check I've done the right thing, I will print out statistics. So hopefully the min-max values are now between 0 and 1 if I've done it right. So the key thing here is these operations. So x has lots of columns in it. Each of these operations are done per column. So nothing complicated. It's just doing this operation, having the formula that rescales my data, and hopefully it's worked. So let's have a look at this. Okay, what error message I got? Name X is not defined. That's because I haven't run the previous cell. Now I should be fine. A few general messages which you get out in Jupyter, but what you will see is it looks all good, right? So I've got this new data set. The min values are all 0, the max values are all 1, and they're scaled in between the two. Right, so a really nice thing to remember to do, rescale your data set. Okay, so I'm going to add another code line here. What we're going to get onto now is actually starting to build that KNN algorithm. But to do this first, we need to split our data between training data and test data. So we're going to train the model, obviously, on the training data. We're going to hold out some data so we can test it and validate it on unseen data to give it a fair test. Right, there's various ways you can do this, but scikit-learn is a really nice package because it provides lots of these things for you. So we're going to import from the scikit-learn library something called sklearn model selection, and we're going to import a function called testTrainSplit. Ooh. Okay, so what this does is it automatically and randomly splits the data between a training and test set for us. So what we're going to have is xtrain, xtest, ytrain, ytest. So these are going to be the sets that come out. And then I'm going to call this function, which is available to me. And then I'm going to first input is the data set, the input data set. I'm going to give the normalized data set. The second one is the whole vector of the target values. The next thing we put in is something called test size, which is actually a percentage they're looking for as a decimal. So if we say 0.2, what we're meaning is 20% of the data is going to be held out for testing. And the final thing you can do, which is always useful when you're testing your code, is you can provide a number called random state. It can be any number, 1, 2, 3, it can be 20, it can be any number you want, integer number. And what that will do is basically set the seed of the random number generator. This means even though the train test split will generate you a random pull of test data from the whole set, if you provide the random state, then it will do the same each time. So for repeatability, it's really useful. Otherwise, you're kind of working out whether it's just randomness or something's fundamentally changed in what you're doing. So if we run this, that should all run fine. Nice little tick. And so our data should. So we can even look at. Okay, what does this look like now? Oh, we can do shape. Right. Okay, that's not a thing. Sorry, it's not a function. So you can just call shape on a data frame. So we'll see now we have 334 and there's 7 columns. And then equally, if I looked at stest, the second one would be 836. So we've got a split. Those two would add up together to the full size, 4,177, I think. Okie dokie. Okay, so first thing we're going to do now is we're going to build a single KNN model for a fixed value of k. So we're going to specify that we're going to look at the value over only k equals 10 nearest neighbours and use that for our regression prediction. So we can find most of the packages in scikit-learn, or most of the algorithms in scikit-learn. So we import sklearn neighbours is where the neighbour algorithms are, and then this one says K-Nearest Neighbours regressor. So if you're doing classification, you obviously would pick classification. Very similar setup, and we'll be covering it elsewhere in the course. And then we're just also going to put in metrics, import mean square error. The fact that it's not giving me an autocomplete suggests I've missed something. There we go. So sklearn also has these things called metrics, and mean square error is a way of evaluating a particular error in your model over the left out set. We'll see how we use it in a minute. So actually implementing models quite easy. We're going to set a variable to k equals 10, and then we're going to define a KNN model by calling the function K-Neighbours regressor. We're going to set the number of neighbours equals K, and then we're going to fit it, which requires you to put X train and Y train. So we're giving it the labelled values. You can always tell if a function is a supervised learning algorithm or not by whether it just has X in it, and it will just be unsupervised. But if it's got X and Y, it means it's got labels with it. So it's an indication that this is a supervised learning algorithm. And so this will build the model, and then we can predict, once we've built this model, we can predict the values using KNN model. And then remember the function predict, and then we want to use the test data. So what this will generate, it will take the test data input and it will predict values from the model. We're then going to go and compare that against the y-test data that we already know to give us an idea of how good our model is. So the root mean square error, the square root of the mean squared error, can be then calculated, here we go, by using that function and then putting in y-test versus predicted values. I think that should be everything. Okay, let's run that model. Okay, what's the error messages? Cannot import name mean square error. Mean squared error. Okay, there we go. Perfect. Right, so ran nicely that time. Yeah. Problem is, computers always do what you exactly tell them to do. Haven't worked out how to know what you're really thinking. So we've calculated root mean square error, so we can see what that is. And you'll see it's 2.345. So on average, the average error that we have is it's just over 2 years, or 2 rings that we're missing by. But that's, how good is that? How does it compare over the whole training set? Probably more useful to plot it out. So what we're going to do now is we're going to import matplotlib, a really standard plotting tool. Lots of good examples online. So lots of different sorts of plots you can do. We're going to do a simple scatter plot. And what we're going to plot is the predicted values. That's gone wrong. Against the test values that we know about, and we'll plot them on a graph. So ideal is going to be straight down the middle on a perfect line where the two are equal, and the scatter plots will be deviated either side of that, showing the variation away from perfect. Probably easier to show you, so let's do that. So we're going to fire up a matplotlib figure. We're going to have figure size. Figure size is equal to 6.4. And then we're going to plot a scatter plot of predicted values and also y-test. Just to make a nice colour, we will have spring green, just to lighten the day a bit, and then give it a little bit of transparency so that if any are overlapping, we can see them. So let's have a look at what that looks like. What you'll get is a plot below, and we're going to also now add in a line which shows the perfect fit, so we can show the deviation away from that line. So to do that, we're going to first make a perfect line. I'm just going to hard code this, but a perfect line is going to live between 3 and 23, and there's going to be 2 points. We just need 2 points. So this basically makes a vector or one value at 3, one at 23. We are going to also plot perfect line against perfect line. We're going to make this a dashed line that's black, and K indicates black. I'm going to make a slight alpha so we can see through it as well. We can also add a title. That's the standard stuff, but always good to do. Model validation with K equals 10. And we're also going to set some limits for the x-axis, 2 to 19. And then we're going to put some labels on our axes as well. So x label, we're going to do predicted. And then on our y-axis, we've got test data, true data, sorry. So this is the truth. And so what we've got here is we've got this perfect line that if we had the perfect machine learning algorithm, everything would sit perfectly on this line. But you'll see it's not perfect, and it shows some fairly significant variation away from this line. So basically the root mean square error is that the average distance from any point here to the line is 2.3. So in the notes when we were walking through the K-Nearest Neighbour algorithm, we said there's an additional step that you can just run it for a single value of k, but how do you know it's optimal? When k is very small, we tend to overfit because we rely on the data at a single point. When k is too large, we essentially smooth our data set too much, so it can't pick up localized features. So the real question is k equals 10 a good value? And so we can look at that now, and we can see if we can build a better model by tuning k. Okay, to do that, it's much of the same really, but what we need to do is we need to evaluate our model via calculating mean square error for different values of k. So what we're going to do is we're going to set up a range of values, and we can do this using numpy's function. And we're going to go from 1 to 125, and we're going to do it in one-step intervals. So we're going to test this model with k equals 1, k equals 2, k equals 3, all the way up to 125. And then we're going to have a list, which we're going to make an empty list to start with, where we're going to store the mean squared errors for each of those values as we calculate them. And then we simply have a for loop where we loop through each of the values of k. And so for each of these, I probably don't need to type it out again, what we're going to do is we are going to build a model, and we're going to basically vary nearest neighbours through each step. So we're going to train it every single time. For this value then, we're going to again call predict vals equals this KNN model, so exactly the same as last time, dot predict, and we're going to call x test again, so exactly the same as last time. And then what we're going to do is in the list we are going to store the mean squared values. So amend basically just adds this value that you're going to give it to the end of the list that you've already got. So you're going to accrue values as you loop through each of the k values you've tested. So mean square error, you're going to get y test predicted vals. Have I closed all the brackets? That looks good. And then I'm going to try and look for the optimal, if I can spell it, k, which will be k where I want to find out the entry of mean square error, which actually gives me the smallest mean square error. So argmin will give me an index, so it will give me the index in mean square error list, which returns the smallest mean squared error, and then I'm going to find the k value associated with that, and hopefully we can print that out. So let's run that. Hopefully it shouldn't take too long. Okay, so what it's come out with is k is 15. So actually 10's a pretty good estimate. And we can, what else can we do? We could look to see, so in mean square error, we could look at 15. And we could see what the value of it is. So to compare it to the last time, we need to take the square root. So it's 2.345, which is very close to the value for 10. So to see what happens to the mean square error, we're now going to plot out all the values against k and the mean square error, so we can see how it varies. The mean square error varies with k, not just for the two values we picked out there because they look pretty close together, but across all values from 1 to 125. So I'm going to just get rid of this value here, and I'm going to replace it with a plot. So instead of you waiting for me to type it out, so what we've got here, we've got a new figure, and then we're going to plot k versus mean square error in blue with a bit of transparency. Then we're also going to have a scatter plot, which gives the optimal k, which I've computed above, and the mean square error. So I'm going to put a dot where the optimum lives. And then on the bottom axis, we've got K, so the number of nearest neighbours, and then on the y-axis, we've got mean square error. So let's have a look, see what this looks like. So this is pretty typical for this kind of plot when you're tuning a hyperparameter. So what we see is the optimum K equals 15 is down here, but to be honest, any value between 10 and 20 would be pretty good. And what you would notice is these actual values would vary a bit with slightly different test data, because it's dependent on the test data. So you don't have to be really precise about which one's the minimum. It would change slightly, but you can see in this region you get a good parameter fit between 15 and 20. What you see is when you reduce it, basically you're overfitting the model, so it doesn't generalize particularly well away from new unseen points. So that's something you'd have to guard against. And then as you go to much larger neighbours, essentially by including the average over too many of its neighbours, you're including effects which are too far away from a new point, and effectively you're smoothing the output, and so you get an increase in error. So really good thing to know how to do. By running the model and validating it multiple times, you can actually pick these hyperparameters K for K and N. You'll see different other parameters in other algorithms that you have to pick, but really good to understand how you can actually learn what you should put in these kind of sometimes abstract feeling parameters that you get with machine learning models. And so just to finish off, as we've already said, you will see that the error is approximately 2.34. So just to interpret what that is, and it's useful to think back to the application, that means if you give me a whole set of measurements which are easy for me to measure about sea snails, then I can give you a prediction which gives me, I can expect an error on average about 2 years, just over 2 years, in predicting the number of rings and hence the age of a sea snail. And a really important question to ask yourself before you say, well, that's not actually very good, and the model doesn't look like it fits particularly well. Like when you see plots like this, you kind of normally expect to see a better model if you're going to really be reliant on it. But a really important question to ask yourself, is the model good enough? Because often, if you can get away with using K and N, it's really simple. It's quite easily interpretable, i.e. you can find predictions that look like what you're trying to predict. So there has an element of explainability via example to it. So if you can get away with a simple model like this, it's a really good question to ask yourself. Is a sort of estimate or error within 2 years good enough for your application? If it is, then happy days, you don't need to do more. If it's not, then you need to think more cleverly about how you're going to improve your machine learning model. And there are lots of other options which we're going to cover in this course.